S3, S4 physics, Ohm's Law. Ohm's Law refers to the relationship between potential difference, voltage, current, and resistance. Ohm's Law can be checked in the lab using a power supply, a voltmeter, an ammeter, and a resistive component. And within an SQA assessment, you may be expected to draw this circuit or to comment on it. The circuit could be set up as shown on the next slide. So here we have our power supply, which is our cell. Just here, we have our resistive component, meter Y and meter Z. You could be asked which of these meters is going to be the ammeter and which of these meters is going to be the voltmeter. Remember, current is always measured through a component, so this one is going to be our ammeter, and voltage is measured across a component, so this one's going to be our voltmeter. This is our supply voltage. Potential difference in the supply is varied, and in each new setting the following readings are taken. We measure the current from the ammeter, remember that's meter Z, and we measure the potential difference from the voltmeter. Again, you could be expected to use a set of results from a question in order to determine a relationship. A possible set of results is shown in the table below, and in order to determine the relationship, we'd expect to put this onto a graph. Analysis of the data can be carried out numerically using P equals IR, or it can be carried out graphically. Numerically, we divide potential difference value by the matching current value. Graphically, we plot a line graph of the potential difference against the current and draw a line of best fit. Remember, potential difference is what's changing, and then the current changes because of what we do. In numerical analysis, 10 divided by 1.3 gives us 7.7, 25 divided by 3.25 gives us 7.7, 15 divided by 1.9 gives us 7.9, 30 divided by 3.75 gives us 8, and 20 divided by 2.55 is equal to 7.8. So remember, each of these are R is equal to V over I. Now we can see a general trend within the answers. What we could do is add all these up and find an average. The trend is in the answers is to give a value that's approximately the same every single time. We would normally write this with the statement, voltage divided by current is equal to a constant. In this case, the name of the constant is called resistance. This isn't always the best way though, because we can see we get lots of different values. Perhaps a better way, using the same possible set of results, is to draw a graph. So here's our set of results. We're going to plot this onto a graph and then find the relationship that way. Okay, so we have our results on the top right hand side here. We're going to use those to plot the graph. Current and voltage. Current is going to go on the x-axis. 1, 2, 3, 4. Current in amperes, which means each of these little divisions is equal to 0.1. Our voltage is going to go on the y-axis, 5, 10, 15, 20, 25, and 30. So start plotting here. 1.3 amperes goes to 10 volts. 1.9 amperes goes to 15 volts. 2.55 goes to 20. 3.25 then goes to 25. And 3.75 goes to 30. So we're going to draw a best fit line across here. We can see that it's going to be a straight line, but for Ohm's law, we should see a directly proportional relationship, which means when we draw the straight line, it should go through the origin. We can then use the gradient of this graph in order to determine resistance. So in the graphical analysis, the line at best fit should be a straight line which passes directly through the origin. This means that the potential difference is directly proportional to current, and this is a learning outcome at National 5. The statement can also be written as voltage over current is equal to a constant, where the name of the constant is resistance. Hence, R is equal to V over I. To calculate the value of the resistance, you could find the gradient of the line of S fit, and this is National 5 content. But not all conductors will give a straight line graph passing through the origin, and that's because for some conductors, as the amount of current passing through them increases, the temperature of the component also increases, and this affects the resistance. The graph below is for the conducting wire in a filament lamp. So we can see that the gradient of the graph is changing. As we go through, here our gradient is smaller, and then it's getting bigger, and then it's getting bigger still here. So the gradient of the line, remember the gradient of the line is the same as resistance here, is much bigger than the gradient of the line at this point. So here we've got a smaller resistance because we've got a smaller gradient. Here we've got a larger resistance because we've got a larger gradient. In order for you to calculate what these values of resistance are, you would use R is equal to V over I, using the values of voltage and current for that particular point. What you may be asked to do in the National 5 assessment is to determine what is happening to resistance by using these values. A component like this, where it doesn't have a directly proportional relationship between voltage and current, is known as a non-ohmic. So the graphical analysis this time tells us that the resistance of the conducting wire in the filament will increase as the potential difference across it is also increased. V over I gives a greater number, that is the resistance when the calculation is carried out further from the origin. A similar analysis could be carried out to show the resistance of a conductor is likely to increase with temperature. For example, with the thermistor, which is a temperature-dependent resistor. So here's a past paper question. Both circuits are used to determine the value of resistance R. Which row in the table identifies meter X, meter Y, and meter Z? Well, if we are calculating the resistance, determining the resistance directly across a component, then this meter must be an ohm meter. In this circuit, we saw this before, we have a supply, a resistor, and two meters Y and Z. Meter Z is measuring in series, so that must be our ammeter. Meter Y is measuring across in parallel, so that must be our voltmeter. So we're looking for ohm meter, voltmeter, ammeter, which is A. Here's another circuit which is similar. It was looking at the current rules as well. Student suspects that ammeters may be inaccurate. Ammeter 2, A2 is shown to be accurate. Which of the following circuits could be used to compare the reading of A1 and A2? So if we want to look at the values as a comparison, then we must be looking at a circuit where they're equal to each other. If we look at circuit A, ammeter 1 and ammeter 2 are measuring different values of current because the current will vary with the resistance. That's Ohm's law. Circuit B, however, is a series circuit, so theoretically current A1 and A2 should be the same. So at the moment, this is our most likely candidate. We look at C. A1 is putting across the supply. That's connected wrong altogether because an ammeter should be connected in series. So C must be wrong. We look at D. Again, A1 is measuring the current, which is coming from the supply. A2 is measuring the current going through R2, so they're not going to be the same. And then in E, again, we have A1 put over the component instead of put through, so that is connected incorrectly. So our answer must be B. In this question, the lamp is connected to a constant voltage power supply. The power supply is switched on. The graph shows how the current in the lamp varies with time. Which row in the table shows what happens to the current and the resistance of the lamp between 0.05 seconds and 0.45 seconds? First of all, it'll be useful to identify our points. So here is our 0.05 seconds, and here is our 0.45 seconds. Look at the value here. Here's our time. We can see the current is high. And then at 0.45, we can see the current is lower. So current decreases. So that's right. That's right. These ones must be wrong. Ohm's law says R is equal to V over I, which means that as the current is going up, the resistance must have gone down, or in this case, as the current has gone down, the resistance must have gone up. So this is correct and this is wrong. It tells us the answer must be A.